we will see later. Programming of FPGA, we will see how to program the FPGA. How to program, configure the FPGA to implement circuit. So far we have mapped the circuit onto the FPGA fabric. Now is the technology mapping. The process of converting circuit in one representation into a representation that corresponds to a physical components. FPGA components, what are the FPGA components now? LUTs, gates, gate level, see circuit diagram, full ladder circuit if you draw, XOR gates, okay, AND gates, OR gates. So how to, but in FPGA there is no XOR gate, AND gate. Inside the FPGA we do not have these things. Inside the FPGA what is there? LUTs, RAMs, DSPs, these blocks are there. We have to we have to map this. We have to map this, whatever logic circuitry you have to map to that components. Okay. So mapping is all gates will be mapped to LUTs. Okay. Memory block, memory array declarations, the storage in the arrays you will write in the program. Okay, data storage. So that will be mapped to block RAMs. Okay, then multiplications will be mapped to DSP. If any multiplication operation is there, that will be mapped to DSP function. But we need to some way of configuring each of component behave as desired. How to store the two tables in LUTs and how to connect wires in a switch boxes we will see. Include flip-flops in a fabric to control programmable components. Need a way to select the mux. So we are, I told you this CLB, basic CLB, either we can get the output combinational, pure combinational or registered output, but that is through by selecting this multiplexer. That means multiplexer selection is a programmable. Multiplexer selection is programmable. That means either we can select pure combinational output or we can select registered output. Yeah, that is a flip-flop. There is a one, that is the one switch is there, one switch is required. That by using that switch we can select either combinational or we can select registered output. But this switch is here technology. Technology I told initially. What are the technologies? Fusing, anti-fusing, ROM, PROM, EEPROM, or flash memory or SRAM memory. But SRAM memory is the latest technology now. Okay. So this flip-flop here, whatever it is shown, that is one SRAM cell. SRAM cell. If you write 0, it will select multiplexer 0 input. If you write 1, multiplexer 1 will be selected. Okay. If you want to select either multiplexer 0 input or multiplexer 1 input, that is a combinational circuit input or flip-flop output, that is a registered output. So that is a programming. Programming is, what is programming here? Programming of that cell. That binary bits you are going to generate, that binary bits, so it going to sit into that cell. Okay. Yeah. Now this also interconnection I just discussed, this fabric, but the junctions are there, no, these junctions, the junctions are interconnections. These junctions are interconnection, that should be programmable, actually it will be programmable. Interconnection is programmable. If you write 1, it will be connected. If you write a 0, it is not connected. Okay. So all the cells will be present there, memory cells. All SRAM cells are going to present at the interconnections. Okay. So if writing 1 to that cell, the connection will be made. If writing 0, disconnection, open. Then FPGA is programmed with a bit file, binary file. Last finally after writing Verilog code, then after simulation, synthesis, everything you have done, finally you are going to generate bit stream, bit file. That bit file only it is going to be programmed with the FPGA. That bit file only it is going to sit all these memory cells. Okay. The bit file whatever you are generated and programming, that bit file it will go sequentially and it is going to store in all these memory cells according to your logic circuitry. So, here file containing FPGA program with bit file containing all information needed to program the FPGA, contains bits for each control flip flop, that is the control flip flop. Also contains the bit file for fill LUTs. I told you, LUT inputs you have to store for according to your functionality. First initially I discussed full adder sum, full adder carry. So, that bits are there, So, those bits also will be stored. That bits will be, it will be stored in that input flip flops, input storage cells of the memory. Okay, we will see. So, but how do you get the bit file into the FPGA? So, more than 10k LUTs, LUTs are 10,000 or maybe 20,000, 100,000 LUTs are there. How that bit file will go into that FPGA and it will store. Okay. So, if you see, so because these are all CLB, in each CLB LUTs are there, but these bits, how these bits will go and store, how many pins are required to store these, how to store these bits into each of these CLBs. Okay. So, because here all CLBs are spread across the chip, but how do we store the bits into this? How to store these bits? How do we store these bits into this box? How do we store these bits into this box? That bit file. Okay. So, that will be stored in the form of a scan path. Okay, this path. Configuration bits input of here, it will go like this. In a scan path, it will go and it will store. In a sequential manner, the bit stream will go inside the FPGA in the scan path, then it will be stored inside the FPGA. It will not go completely in parallel fashion, bit stream. Okay. So, because that the huge number of CLBs, the bit stream also very lengthy, they make a huge shift register out of all programmable components, LUTs, control flip flops, and shift in bit file 1 bit at a time. That is why this configuration, it takes some time. That delay we call it as a configuration latency delay, initial delay. To configure the chip, that program the chip, it takes some time. Why it is taking time is because that bit stream, it has to go in this fashion across the FPGAs. Okay, example also, if you see simple example. So, this is full adder, the simple full adder, it is not working over. Okay, this is full adder, if you see, this is a full adder. So, the full adder lookup table input, what do you have to store? The sum or carry, the sum bits, all the sum bits you have to store in this, all carry bits you have to store in this. Okay, and also one control flip flop is there. So, this is for selection of combinational, because this is the combinational circuit. So, how many bits you have to program this now? 8 bits per sum and 1 bit per control flip flop. Similarly, 8 bits per carry and 1 bit per control, 9 bits, total 9 bits you have to generate. Total 9 bits for full adder implementation, complete full adder implementation including sum and carry, how many bits? 18 bits. Okay. So, it will go like this, that 18 bit stream, 1 bit at a time it will go, bit by bit it will go like this. Okay. That is all, that is a programmed. LUT is programmed now, it will function like a full adder. But this is a very simple circuit shown, but entire FPGA also programmed in this fashion only. Okay. Right. Reconfiguring a FPGA is slow. Shifting 1 bit at a time not efficient. Reconfiguration. So, bit files can be greater than 1 megabyte. Eliminates one of the main advantages of reconfiguration. RC is reconfigurable. So, partial reconfiguration with shift registers, entire FPGA has to be reconfigured. Solution, I think problem first you should understand. You understood the problem? Huh? Reconfiguring the FPGA is slow, but reconfiguration means If you load some bit file, then later you want to modify and again you have to load new bit file, it takes time. Okay, and runtime we cannot do at all. Real time, runtime we have to off and again load. Runtime we cannot change, but the FPGAs are actually runtime reconfigurable. Okay, that means partially reconfigurable, dynamic reconfiguration. This is the features are available, but this will not solve that. It will not use that features here. If you do like this bit by bit, if you reconfigure, this eliminates one of the main advantages of RC, partial reconfiguration. With the shift registers, entire FPGA has to be reconfigured. That takes time. What is the solution is, in Vertex 2 allows columns to be reconfigured, and Vertex 4 allows custom regions to be reconfigured. Requires a lot of user effort, better tools needed. So partial reconfiguration we can do. Partial reconfiguration. We need not reconfigure the entire chip again. So already we reconfigured. You just modified only 1 or 2 bits. If 1 or 2 bits means that 1 or 2 bits only you have to reconfigure. Why do you need to reconfigure entire chip again? Okay. So that partial reconfiguration is possible only in 1 or 2 the latest FPGAs, not all FPGAs. So Vertex 2 and Vertex 4, that is where this Vertex 4 also not latest, was. So Vertex 7 is there, 8 is there now. LUTs with many inputs can implement large circuits efficiently. Why not just use LUTs with many inputs? Just that we discussed initially. High flexibility in routing resources improves routability. This is a trade-off. See, why not use LUTs with many inputs means? So, because small circuits, the LUT inputs will be underutilized, not utilized. So, if it is a small LUTs are there, we can interconnect and we can implement large circuits. Okay. So, what is the optimal number of inputs are required? That only that is present inside the FPGA. Optimal. Most of the logic circuit that is implemented with, let us say, 4 input. So, 90% of the circuit you are implementing with 4 input means 4 input LUTs is present. In some FPGAs internally it contains 3 input LUTs, 4 input LUTs, even 5 input LUTs, like the different input sizes also present. But some FPGAs only fixed size. For a Zinc FPGA, it 6 input LUTs, all are 6 input LUTs. Okay. High flexibility in routing resources improves routability, that we know. Flexibility, we see in switch matrix, connection matrices. Okay. So more flexible means routability is more. So we can route 100% easily. Why not just allow all possible connections? Answer: architectural trade-offs. Anytime one component is increased or improved, there is a less area of other components. Yeah, the trade-off you have to maintain. So that means if larger LUTs, less total LUTs, less routing resources. More number of, see how many LUTs, 100K, 200K or 500K or 1000K LUTs. What is the size? Size is if more number of LUTs if you place inside the FPGA, but placing of other logical blocks like a memory blocks, DSP blocks, routing channels, the space will be reduced. This is a trade-off you have to maintain, that's all. Okay. Similarly, more block RAMs, less LUTs and DSPs, more DSPs and less area for LUTs and less block RAM. That is the optimal number, some area for block RAMs, some area for DSP and most of the area for LUTs. So like that, and also some area for routing of the wires. Like that it is planned inside the FPGA. Okay. Yeah, if you see this one question, simple question, determine best LUT for following circuit. That best LUT size, either we can go for 4 input 2 output LUT or 5 input 2 output LUT. Which one is best? Either we can choose first one or second one. So first one is constraint also there. The constraint is a delay 2 nanoseconds, and third one is a delay is 3 nanoseconds. 5 inputs are there, but delay is more. But first one is 4 inputs are there, delay is less. But which one you will choose? And one more constraint is, first one is it will take number of transistors, that is area. Number of transistors are area. The area of the first LUT is 192 transistors and 5 input LUT 384. How do you get that 192? Now we are getting that 192, 4 input LUT. Why it is multiplied 6 multiplied by 2 power 4 multiplied by 2? Number of transistors. Assume each SRAM cell is 6 transistors. 4 input means how many cells? 2 power 4, 16 cells will be there. Each cell it stores each cell it stores 2 bits. That means 2 RAM cells are required. 2 RAM cells. Each RAM cell how many transistors? 6 transistors. Okay, 6 multiplied by 2 power 4 multiplied by 2. That is 192 transistors for each LUT. 4 input LUT. 5 input LUT 384 transistors area. Okay, area. This is area. That is the time. Then area and time optimization. Time optimization delay 2 nanoseconds and 3 nanoseconds. Area is 192 and 384. Now tell me which one is better for mapping of this circuit, combination circuit, either 4 input LUT or 5 input LUT in terms of delay or in terms of area. You see the solution. This is the solution. 5 input LUT, suppose if you use 5 input LUT if you use, so we require 2 LUTs, because here 4 are there, here 3 are there, 3 inputs and 4 inputs, 2 LUTs are required. 2 LUTs means total area 768 transistors are required. Total area is 768 transistors. Okay. Delay is concerned 6 nanoseconds. Why 6 nanoseconds? Not 2, by using 2, but it is one output of one is connected to input of other one. So if you see this takes 3, this takes 3, first one, this one is takes, I think it is not visible. This mouse is not coming. Yeah, this one takes how much time? This LUT 3 nanoseconds. This LUT will take 3 nanoseconds, but should not say that 3 plus 3. This because here this is taking 3, and this output of this is connected to this gate. Okay, so that's why this 3 plus 3 are. Otherwise, if it is both are in parallel, only 3. It is a cascaded connection. So 6 nanoseconds. Okay. Next one, if it is a 4 input LUT, the 4 input LUT, because here 384 only, 192 plus into 2 transistors, and the propagation delay is 4 nanoseconds. Now 5 input 6 nanoseconds, 768 transistors, area is more, delay is more, 5 input LUT. If you go for 4 input LUT, area is less, delay is less. So then which one is better? 4 input LUT is better. Okay. Now this one, determine best LUT for the following circuit. Which one is better, tell me for this? You decide and tell me. So first apply 4 input, then see what is the transistors and delay. Then next you apply 5 input and test number of transistors and LUT and tell me which one is better. First is 4 input. If you take 4 input, how many LUTs are required for 4 input? 2. 2 means 2 into 192. 2 into 192 transistors, 384. 384 transistors are required. Delay 2 plus 2, 4 nanoseconds. 4 nanoseconds delay. If it is a 5 input LUT, If it is a 5 input LUT, how many LUTs are required? 1 or 2? 5 input LUT, if you use one LUT is sufficient, 2 input or 2 LUTs I have to use. If it is a 5 input LUT, 5 input LUTs, only 5 inputs only there, no? Yeah, how many inputs are there in this circuit? In the circuit, how many inputs are there? 5 inputs. One single LUT is sufficient. 5 input LUT is sufficient. If we use 5 input LUT, number of transistors are 384. Okay. Delay 3 nanoseconds. So transistors are concerned same. Transistors are, whether you go for 4 input or 5 input, same number only, 384 only. Okay. But delay wise, there if it is a 4 input, it is 4 nanoseconds. If it is a 5 input, it is 3 nanoseconds. So it is faster. So then you have to go for 5 input LUT. Here 5 input LUT you have to go. Okay. Yeah. This is another circuit is there. Okay. Large LED is fast when using all inputs, waste transistor otherwise. Okay. Fast when using all inputs. That is the 5 inputs, all 5 inputs we are using, it is fast. Okay, otherwise it is waste. You must also consider total chip area. Wasting transistors may be okay if there are plenty of LEDs. Vertex 5 or vertex 6, vertex 7 also uses 6 input LUTs. Kintex also, it is using Kintex, Artex, all this Zinc FPGA, it is using 6 input only, 6 input LUTs. Vertex 4 uses 4 input LUTs. Okay, right. How to design FPGA fabric? There is no overall best. Design fabric based on different domains. DSP, then DSP one type of application, DSP application, and high performance computing, one type of computation, high performance computing and embedded system. These are the 3 categories of applications. One is DSP type of applications, and second category is high performance computing applications, parallel processing, high speed operations, high performance computing, and third is embedded type, embedded computing, embedded system type. So for Xilinx there are 3 different types of devices. One is LX, other one is SX, and third one is FX. Yeah, hello sir, Bhaskar ji. You are starting now. I'm going to complete maybe at 1 o'clock train only. So yeah, I'm still in the class. Okay, I'm going to finish within 4-5 minutes. Possible I will reach otherwise okay sir. Thank you. Okay, Bhaskar. Wait for a few minutes. I am coming. Okay, LX for logic, SX for signal processing, and FX for embedded systems. When you are selecting the FPGA, you have to see this LX series or SX series or FX series. Depending upon the application, you have to choose that the corresponding FPGAs. That's all. Okay, right. I will close this session now. So then maybe meet again in the afternoon. Afternoon I am going to again this FPGA related stuff only, but one processor design I am going to explain. Complete processor design. Okay. So One is DSP type of applications, and second category is high performance computing applications, parallel processing, high speed operations, high performance computing. And third is embedded type, embedded computing, embedded system type. So, for Xilinx there are three different types of devices. One is LX, other one is SX, and third one is FX. Yeah, hello sir, Bhaskar ji. You are starting now. I'm going to complete maybe at 1 o'clock train only. So yeah, I'm still in the class. Okay, I'm going to finish within 4-5 minutes. Possible I will reach otherwise okay sir. Thank you. Okay, Bhaskar. Yeah, wait for few minutes. I am coming. Okay, LX for logic, SX for signal processing, and FX for embedded systems. When you are selecting the FPGA, you have to see this LX series or SX series or FX series. Depending upon the application, you have to choose that the corresponding FPGAs. That's all. Okay, right. I will close this session now. So then maybe meet again in the afternoon. Afternoon, I am going to again this FPGA related stuff only, but one processor design I am going to explain. Complete processor design. Okay. So the architecture way of the central processing unit and the graphics processing unit, comparing their structures, cores, memory architectures, and processing capabilities, we will see. Okay, little bit. So CPU is constructed from billions of transistors. Okay, the CPU can have multiple processing cores. Okay, and is commonly referred as a brain of the computer. Okay, it is essentially to all modern computing systems, as it executes the commands and the process needed for your computer and operating system. You know, CPU is main component of a computing system. Okay, it contains multi-core CPUs, single core CPUs, the different architectures. Okay, VLAW architecture, pipeline architectures, parallel processing architectures, different types of processor cores will be present. So GPU is, what is the difference, main difference between CPU and GPU? Okay. CPU is actually internally it contains the highly sophisticated computing architecture is present in the CPUs. Cores are maybe multiple cores, but cores are limited, maybe octa core, 8 cores or 16 cores maximum. Okay, 16 cores, 8 cores, but each core is highly, each core capability is almost high processing computing capabilities there in each core. There may be a floating point or maybe complex operations. It can be done very fast. Okay, in single cycle it can be able to compute complex operations, highly sophisticated architecture with the pipeline and everything will be there. But whereas in GPU contains multiple processing units, multi-cores, thousands of cores is going to present. CPU is only maximum 16 cores or 8 cores processing, but each core is high computing power, high processing power for each core. But whereas GPU cores, thousands of cores, but each core is limited processing power. Each core processing power is limited, that is, so a simple processing element is present in each core. So maybe the GPUs we can use for graphical processing, see image processing application, video processing, or machine learning these days, okay, pixel processing. So, there each core is a simple processing, but thousands of processing elements is present in the GPU. Okay. So, these thousands of processing cores is going to work in parallel. That means simple processing only, maybe multiplication and addition operation only. Addition, subtraction, multiplication, this is only simple operations, integer operations or maybe floating point operations. But whereas processor cores are not like that. Internal architecture highly pipeline, highly processing, super scalar, super pipeline. Okay. So, that type of architecture is in the CPU cores. Okay. So, GPUs or graphic processing unit is a specialized electronic circuit designed to rapidly process and manipulate memory to accelerate the creation of a digital image, because GPUs have thousands of smaller cores. Okay. So, compared to CPUs, GPU architecture is optimized for parallel processing. Okay. So, GPU can handle multiple tasks simultaneously and are faster at graphical and mathematical workloads. Okay. Thousands of operations can be done in parallel in GPU architectures. Okay. Yeah, see, they have an example just for easy understanding. CPU is like latency, optimized latency. CPU is like one high speed car. Okay. CPU processing is high speed car. Okay. So, optimizes latency. We can CPU is very less number, but it can do very fast computing, faster car, speed, high speed. But GPU, if you take throughput, see GPU throughput, I do not know whether it is multiple, okay, maybe processing, but that latency, optimize latency. So, that means that can be through GPU, we can travel through CPU. See, it is a very fast, but limited persons only can be traveled, very high speed latencies. Okay, multiple people can be placed one place to other place. Okay, multiple persons. Okay, maybe it can be moved from one place to other place. So, that maybe we can go through a single car with high speed car. Okay, or we can go through a multiple bicycles. Okay, 100 persons you want to transfer from, for example, NIT to Kashipet. You can give 100 cycles. Okay. So, the 100 people will go through that 100 cycles, or otherwise with one car you can very quickly you can transfer each time at a time 5 you can 20 trips the car moves from here and there. So, all 100 people will go. So, that is the analogy here, simple analogy. CPU is like a high speed car. Okay. GPU is also a small processing engine, but multiple processing engines parallel. Yeah, okay. If you see the difference here, the CPU is control unit, it is going to present control circuitry and common controller logic and cache memory, and as well as the processing cores, high speed processing cores like ALU, that 4 ALU, green color ALU, 4 cores. But these 4 cores are very powerful cores, high speed processing engines. But whereas GPU, if you see that green color, so many processing engines are there, CPU cores. Okay. The small processing elements only, that will not that much capable of that CPU, not on par with the CPU cores. This is only simple processing engines, multiplication or addition type of simple operations can only, it can be done with this, but thousands of cores are present in this. Okay. Low compute density CPU, high compute density. Okay. Compute density means multiple operations can be done faster. Okay. Multiple operations can be done in parallel, high compute density. Okay. Thousands of multiplications can be done in parallel in case of GPU. But here multiplications can be done, but limited multiplications with high speed. Only four operations can be done in parallel, but high speed. complex control logic in case of CPU. Then here control logic is okay, inbuilt maybe, but maybe small control logic for each row or each column or each processing element there is a small distributed control logic. Okay. A small control logic, if you see multiple control logics are present in this yellow color blocks, small yellow color blocks. Okay. Then built for parallel operations, many parallel execution units, ALU, graphics, the best known as is a parallelism. And here if you see large cache memory, that orange color block is the cache memory. Okay. Maybe megabytes of cache memory is going to present in this large cache memory in CPUs. But cache memory is also present in the GPU, but it is a very small limited cache memory, small cache memory. Then optimized for serial operations in ALUs, higher clock speeds, so CPUs. And here parallel shallow pipelines, CPUs, shallow pipelines, that is maybe less than 30 stages, but whereas GPU is deep pipelines, hundreds of stages. Pipelining stages are more in the case of GPUs. GPU deep pipelines, hundreds of stages, these are shallow pipelines. Then latency, low latency tolerance, the high latency tolerance here. Throughput is concerned, this GPU throughput is high. Hello? Chalo. Low latency latency tolerance, this is high latency tolerance. Newer CPUs have more parallelism, okay, and here new GPUs better flow control logic because more CPU like. This category more memory access, don't have one-way pipeline, system more. Okay, right, thank you. So this is the main just brief difference between CPU and GPUs. Okay, what is CUDA programming? So because the software program also it should support parallel execution. Okay, the program that you are writing on CPU, the same program we cannot run directly, we cannot run on GPU as it is. Okay, we have to modify the programming structure so that it can be executed parallelly on the GPU. Okay, for that we are going to use the CUDA programming. The Compute Unified Device Architecture is a parallel computing platform and programming model developed by NVIDIA. It enables developers to use GPUs for general purpose processing, offering significant speed up for parallel tasks. Okay. So, okay, I am not going to continue this, I will stop here only. This for just for time, okay, otherwise shall I continue? Okay, no, whatever I planned that I will continue. So, morning I think we have skipped some of the slides, just I will cover just few minutes about that internal one example architecture will take, that is general. I discussed about the FPGA fabric generally. Yeah, this is one architecture. This 7 series FPGA. This is 7 series FPGA. Okay. So, what like Vertex 7, but it is not Vertex 7 family, 7 series FPGA. Vertex 7 is different, this is a Zinc FPGA. Okay. So, in this FPGA, one more fabric component I forgotten, that one more fabric component is processing core also it is present. Processing core, in addition to that whatever we have discussed in the morning, interconnect resources, okay, and interconnection what is called interconnector resources, connections, vertical horizontal tracks, lanes, as well as switch matrices, and also dedicated memory and dedicated computing blocks, DSP blocks, and plus CLBs, and plus one more is processing engines, my processor cores also present. In Vertex 4 FPGA there are 4 processing cores inside. Okay. PowerPC processing core engines are present inside. PowerPC Motorola PowerPC 32-bit RISC architecture, processing cores. That means everything, the processing core, that means CPU. Okay. Or CPU is present, memory is present, then computing logic, CLBs. So, plus interconnecting structure, everything is present inside the FPGA fabric. Okay. So, this is Zinc FPGA, Zinc evaluation, that is the family name, that is Zinc, like a Vertex. So, Zinc. Okay. So, in the Zinc evaluation, if you see the processor, there is again the processor, suppose you want to interface to the FPGA, externally we have to connect the processor core. Okay. But maybe in some FPGA there is an on chip also, like a Vertex 4 there is a processor core, PowerPC processor core, 4 processor cores are present inside the FPGA. Similarly, in the Zinc also there is a processor core, like here ARM A9 processor, ARM processor core, dual core ARM A9 processor core is present. That blue color is the blue color one block, that is ARM processor core. That yellow color one is FPGA fabric, whatever I discussed in the morning, that is FPGA fabric total. Okay. So, this is Zinc FPGA on chip resources. So, here in the Zinc before this glue logic, BRAM, DSP is there, but then later microblaze architecture also there, soft core, that is a soft core processor. It's accelerator 1, accelerator 2, microprocessor, soft core, soft multi-core plus accelerators, that is the next version, that is a microblaze. The next is Zinc. Zinc is dual core A9 plus accelerators, GPP plus accelerators. Okay. Then the future Zinc may be GPP, next generation GPP, and multi-core processors, that P is processing engines like a GPP structure plus accelerators, that type of applications we can implement on the future Zinc FPGAs. This is for future Zinc FPGAs. Now, currently we are using this Zinc FPGA, okay, dual core A9, dual core means 2 cores. Okay. Yeah, if you just see the evaluation, this is a programmable portfolio, Spartan 6, Spartan family, Spartan 6, Spartan 7, then Arctex, then Zinc 7000. Okay. So, here Spartan 6 family we can use for image processing, safety and security, the precision control, sensor fusion, any to any connectivity. So, for all these type of applications are maybe it is suitable. So, mainly image processing applications, Arctex 7 and Zinc 7000 FPGAs are more suitable. Okay. The next is safety and security features are included in Spartan 7, Arctex 7, Zinc 7. Then precision control also it is present all these 3 families, and sensor fusion is present in Spatron 6 onwards, and then any to any connectivity it is there in all FPGAs. So, this Kintex are, so the Arctix family or Kintex family is there in the 7 series FPGA, Zinc 7000 FPGA. This is processor centric platform, that is dual core ARM processor plus FPGA fabric is there in the Zinc SoC. SoC is system on chip. So, offers software, hardware and IO programmability in a single chip. Incorporates dual core ARM Cortex A9 based processing system, that is a PS, and Xilinx programmable logic in a single device. Then built on a state of art high performance low power 28 nanometers high K metal gate processor technology is used in this 28 nanometer technology based processing engine, and it is Arctix or Kintex 7 based programmable FPGA fabric, 7 series FPGA fabric, and up to see logical cells. Just now morning LUTs we have discussed, CLB cells, LUTs. 6.6 million logic cells are present in this. 6.6 million. Okay. Transceivers means high speed serial communication interface. High speed serial communication interface. So, that high speed serial communication interfaces are from 6.25 gigabits per second to 12.5 gigabits per second rate. Serial communications also present on this FPGA. Okay. So, complete ARM based processing system, okay, that like ARM processor core, complete ARM processor core, how it is we are going to program that ARM processor core outside the FPGA, same similar ARM processor core as it is going to present on the chip. The application processor unit, dual ARM Cortex A9 processor, cache support, fully integrated memory controller, IO peripherals, tightly integrated programmable logic, and flexible array of IOs, wide range of external multi-standard IOs, high performance integrated serial transceivers and A to D digital converter inputs. This is the internal architecture of that FPGA. Okay. See, this portion completely the blue color one, that is processing system, PS. Yellow color one is programmable logic. FPGA fabric is yellow color one. So, the total is one, that FPGA total Zinc FPGA. So, in that if you see this green color, light green color, this is ARM dual core ARM A9 architecture, processor cores. These are the processor cores. That means why processor cores we can run. So, ARM processing language, embedded systems we can implement on the FPGA. So, right. So, C programs we can able to write it, we can develop the application code in C. That C code we can execute on these processor cores. Okay. And yellow color fabric is the FPGA fabric, programmable logic. Here by using Verilog or VHDL, so we can develop the logic and we can implement on this FPGA fabric. Okay. Then this ash color or green color blocks are interfacing blocks. Interfacing blocks like in embedded system, embedded controllers, there will be interfacing like a serial interface. For example, here I2C interface, I2C, SPI interface, CAN interface, GPIO parallel lines, okay, SD card interface and USB interface, DMA interface and Ethernet interface. These are all interfaces are present. This is all type of interface. With this we can connect those devices to this system. Through I2C we can connect any system. Camera, suppose you want to connect, we can connect the camera to this FPGA, okay, or USB, through USB you can connect any device, USB enabled device, you can connect to this system through these interfaces. That means it is a powerful FPGA we can use for in embedded applications with a lot of external communication interfaces plus FPGA fabric and processing cores are present inside the system, this FPGA system. Okay, system on a chip. It is programmable or reconfigurable SoC. Reconfigurable means, so just now morning reconfiguration we have studied. That is why this is a reconfigurable SoC. SoC means system on a chip. System means processor is present here because this is a processor memory is there, memory interface is there, plus on chip cache memory is also present. We can connect external memory, DDR memory, okay, right. So, plus FPGA fabrics, all interfaces, processing system as well as the memory is present, that is why we call it as this is SOC, system on a chip. Complete system we can implement on this FPGA. The internal the details of that block diagram. So, application processor unit, memory interface, IO peripheral interface, interconnect, that is about PS processing system. Program logic is PL, PS and PL. Okay. So, this is internal blocks of the processor core, that ARM processor internal blocks. Two dual core ARM processors are there, each internal there is a arithmetic logic unit ARM Cortex ANN CPU, this is ARM processor core, plus floating point unit, that is a floating point arithmetic operations also we can execute on this processor core. Then memory management unit, we can connect this processor core with external memory, DDR type of memory. Okay, DDR means 4 GB or 2 GB, 8 GB memory we can interface. Then cache memory, on chip cache memory also present here, 32 KB instruction cache and 32 KB data cache memory. Okay. So, that type of processor cores dual, two are there in this, plus L2 cache memory also, 512 KB L2 cache memory, L1 cache memory and L2 cache memory, and then also on chip some memory, small memory is also present, that is a 256K SRAM memory is also present, okay, and 8 DMA channels, you studied DMA, right. So, DMA channels, 8 DMA channels also present. Okay, same thing it is again, once again it is shown here. So, if you see APU, each APU internally contains ARM Cortex ANN CPU, Neon unit, floating point unit, memory management unit, L1 cache. Snoop controller is a cache related, L2 cache, system level control registers, accelerator coherency port, on chip SRAM, DMA controller, general interrupt controller, timers. So, the pins, dedicated pins, 54 dedicated pins, because these pins are shared between multiple functions. So, but external is concerned MIO, so 54 dedicated pins are there, but these are shared across multiple functions. Okay. It can be shared for DMA or USB or maybe SD card or maybe, so the different functionality is there in this. Okay. These pins are shared across multiple operations, multiple functions. Input output peripherals, 2 gigabit Ethernet controllers, 2 USB controllers, 2 SPI controllers, 2 SD card controllers, 2 CAN, 2 I2C, 2 UART, 4 32-bit GPIOs, static memory interfaces, NAND and NOR SPI, quad SPI flash and trace ports. These are all features of this IO processor interfaces for the input output peripherals. Memory is concerned, DDR memory controller, quad SPI controller and static memory controller. These 3 memory controllers are going to present inside the FPGA fabric. This is a DDR memory controller block diagram internally, external DDR memory interfacing. Interconnects are actually internal FPGA fabric to CPU processor core, the interconnections also there. FPGA fabric to the processor core interconnect. That interconnect is primarily mechanism for data communication. Interconnect located within the PS comprises of multiple switches to connect system resources using AXI. AXI point-to-point channels for communicating address, data and response transaction between master and slave clients. So, what is AXI? AXI is a part of ARM AMBA 3.0 interconnect. Okay. So, if you see interconnect features are, the interconnect is based on AXI high performance data path switches, Snoop control unit, L2 cache controller, and interconnect switches based on ARM NIC 301. So, central interconnect, master interconnect for slave peripherals, slave interconnect for master peripherals, memory interconnect, OCM on chip memory interconnect, AHB and APB bridges. So, this is your AXI interconnect. So, this is the AMBA interface, that AMBA is advanced microcontroller bus architecture. Okay. This is for interconnecting a FPGA fabric with processor core. So, in this APB, AHB, AXI, so this is sub interfaces, or maybe these are actually AMBA 3.0, there is in standard 3.0. So, in that these are the bus interfaces basically from AMBA bus architecture. AMBA bus architecture internal sub interfaces. Okay. So, peripheral bus, high performance bus and AXI bus. AXI is here advanced extensible interface. This is a Xilinx FPGA, mainly for Xilinx logic interconnection purpose, this AXI used. Xilinx FPGA fabric interconnection purpose only this AXI is developed. But this is developed by ARM organization only, AXI, AMBA bus. But HB, APB, these are all part of the AMBA only. Yeah, just see this, and quickly I close this. AXI interconnects AMBA, if you see APB, AHB, AXI, ATB. So, in this AXI again 3 categories. AXI is, what is AXI? AXI is, I told you know, this is advanced extensible interface. Advanced, this APB is advanced peripheral bus or AMBA advanced peripheral bus, what is APB? Peripheral bus only. A for advanced we can use, or AMBA we can use. A is AMBA actually. This is AMBA, from the AMBA only this has derived, these 3 bus interfaces. Peripheral bus, AMBA, peripheral bus, AMBA high performance bus. So, but here advanced extensible interface, that means you can also use A, advanced peripheral bus, advanced high performance bus, advanced extensible interface. Extensible, this advanced extensible interface AXI bus, this bus is mainly for interfacing FPGA fabric with the processor core. So, this AXI again divided into subcategories, AXI 4 memory map, AXI 4 stream, AXI 4 light. These are the 3 subcategories of AXI, that is AMBA 4.0. This is AMBA 3.0 is these categories APB, AHB, AXI. Okay. So, if you see the difference, AXI 4 memory map full, traditional address data burst, single address multiple data. Burst transfer operations, if you want burst transfer, then you have to use AXI 4 memory map interface. This is a traditional address data burst transfer, single address multiple data. Burst type of data, burst data is burst data means multiple data, multi data, single address, same single address, multi data we can transmit, DMA transfers. So, this similar to this here, it is again PLB V46 and PCI. Streaming, AXI 4 stream, this is one more subcategory of AXI 4, streaming. This is data only, there is no address, continuous transmission of the data, streaming. Data only and burst, like DSP interface, FIFO, FSL, local link. So, streaming is data only or burst transfers also we can use, data only. The light transfers are AXI light, one more is AXI 4 light. This is a traditional address data, no burst transfer is allowed here. It is only single address, single data only we are going to transfer in AXI 4 light. Okay, you can use AXI 4 light or AXI 4 full or streaming. Any one of these 3 interfaces you can use to communicate with the processor core inside the FPGA with FPGA fabric. Okay. So, each Zinc 7000 device contains same PS with PL and IO resources vary between the devices. There are different types of 7000 series devices, Zinc devices. So, 7010, 7015, 7020, they are dual core, whereas 7007, 7012, 7014, those are one single core only. The PL based is the PL based Arctic 7 series FPGA logic. PL is Arctic 7 only, all FPGAs Arctic FPGA fabric. Then coming to 7030, 7035, 7045, 7100, but here only PL is varied. PL is Kintex based. PL is Kintex based FPGA fabric remaining. So, but the device side, processor side remains same. So, PS and PL can tightly or loosely coupled using multiple interfaces and other signals that have combined a total of 3000 connections. PL can be a separate power domain from the PS, saves power. So, different power up operations also possible, different power modes. Yeah. So, configurable logical block, the PL side, 6 input lookup table, that is why morning we have discussed lookup table size. So, all these FPGAs 6 input LUT, memory capability within the LUT. Okay, each LUT if you want to convert into memory, it is possible, memory capability. Then register and shift register functionality, that means each LUT we can also convert into a shift register. If you want to, you can use as a shift register also, that possibility is also there. You can convert that LUT into a shift register. And cascadable adders. So, for example, ripple carry adder type of adder, suppose if you want to implement 32-bit adder, 64-bit adder. So, that cascading type logic is automation, automatically it will be cascaded. Okay. Cascadable adders also we can create with the help of the LUTs. But memory is concerned 32 KB block RAM, 32 KB, KB is kilobytes here, 32 KB kilobytes of block RAMs. How many are there? We do not know. How many are there in this? Not given. Dual port, okay, and up to 72-bit wide. That means we can increase the width also, memory block. Memory width also we can increase. Width is memory width 8-bit. If we connect in parallel, we can increase the width. If you connect in serial, increase the size. Configurable as a dual 18 KB. So, this is 32 KB, no? So, configurable as a dual 18 KB. We can configure that into 18 KB, dual 18 KB also. We can convert that into two 18 KBs. Or you can increase the 36 to 72 KB like that, we can also increase. Programmable FIFO logic, you can also convert into FIFO. We can use as a FIFO. Built-in error correction and circuitry, that is memory error correction circuitry also built in this. Yeah, DSP slice. DSP slice, we have seen DSP slice morning. So, here 25 by 18 2's complement multiplier accumulator, high resolution, 48-bit multiplier accumulator, 25 by 8 2's complement multiplier and accumulator, high resolution, 48-bit by 48-bit multiplier and accumulator also possible. 25 by 18 2's complement multiplier accumulator or 48-bit multiplier and accumulator. We can configure that DSP. Power saving 25-bit pre-added to optimize symmetrical filter applications. 25-bit pre-adder. Then advanced features like optional pipelining, optional ALU and dedicated buses for cascading. These are some of the features of the DSP. Clock management, high speed buffers routing of low skew clock distribution. Clock will be actually not clock is actually clock managing circuit is going to present, that will distribute the clock across all CLBs in a tree fashion. So, equal length will be maintained, the clock skew will be eliminated. So, low jitter clock generation, jitter filtering, that clock management will take care of this. Frequency synthesis and phase shifting, configurable IOs, input output pins, blocks, high performance select IO technology, high performance decoupling capacitors within the package for enhanced signal integrity. So, this is IOs about input output pins, and a digitally controlled impedance that can be three stated for lowest power or high speed IO operation. High range IO supporting 1.2 volts to 3.3 volts, high performance IO support 1.2 volts to 1.8 volts. That is the IO technology we can use for higher range or high performance. Low power serial transceivers, the serial transceivers, high performance transceivers, low power transceivers are in these devices, low power serial transceivers. High power transceivers are capable up to 12.5 gigabits per second GTX in these devices 303545, but ours is 7020, it is not comes under this category. Okay. High performance transceiver capable up to 6.25 in 7012, 7015. Low power mode optimized for chip to chip interfaces. Okay, 7020, I think serial interface is not there. PCI Express, integrated interface block for PCI Express designs. PCI Express is serial PCI interface. PCI is a parallel interface, PCI bus, but PCI Express is a serial PCI interface logic. Latest laptops all will contain only PCI Express interface only. But compatible with PCI Express base specifications and supports generation 2 5 gigabits per second. Advanced configuration options, advanced error reporting and end-to-end CRC, advanced error reporting and ECRC features. These are important features for the this FPGA fabric, the Zinc 7000 FPGA. Okay. Processor design చెప్పాలా లేకుంటే ప్రాసెసర్ డిజైన్ అంటే ఇట్ విల్ టేక్ ఆల్మోస్ట్ ఒక 1 hour 1.5 hour ఇదే అవుతుంది.